Okay, well, it's a couple of minutes past the hour by my clock, so let's get started. Welcome to the next of the webinars in our Athena X-ray talk series. Before we get started, some of you might be wondering if there's any further news about the mission, given all the messages and the different information that's been circulating over the last few months. I'm afraid there isn't really anything new to communicate at the moment. You will hopefully have seen that ESA have a call out at the moment for members of the new Athena science redefinition team, and the deadline for that is this week. So do consider putting in an application for that if that's something that you might be interested in contributing to. But today we're going to hear some interesting X-ray research in the area of galaxy clusters, and our speaker is Dominique Eckert. Dominique is a senior lecturer at the University of Geneva at the moment. He's previously worked at MPE and at EASF Milan. And during that time, he's done a lot of interesting research, mainly in the area of galaxy clusters. And he also chairs the Athena topical panel on astrophysics of galaxy groups and clusters as well. So over to you, Dominique.
Thanks very much, Judith. And I'd like to thank the ACO and Sylvia for inviting me to give this talk. So what I'd like to do today is to try to give you a small overview of what we've been doing in the past couple of years, especially in collaboration with Stefano Ettore and a few other people who are mentioned here, in trying to understand the gravitational field of galaxy clusters and see what we can do, what we can get from it in terms of understanding the nature of dark matter, and maybe set constraints on any potential modification of gravity on large scales. So just to give you a quick overview of what everybody knows, this is the current cosmological model that we get from observing the cosmic microwave background. And from this cosmological model, then there is only 5% of it, which is this small pie, red pie on the right-hand side, which contains everything we know about in the current universe. Well, it's called baryons, but I mean, it would also include radiation and anything we know about in the universe. And the rest is split between an unknown form of matter that we call dark matter and some repulsive energy that we call dark energy. But here I won't talk at all about dark energy. We'll be focusing entirely about dark matter, because that's something we actually know a lot more about than about dark energy. So this cosmological model has been extremely successful at explaining our observations of the universe's large-scale structure, but there's 95% unknown stuff in it. So it's really fundamentally flawed. So there's a lot we need to do in order to think that we've solved cosmology, right? And one thing that we can do based on the current model is we've been doing in the past years, in the past decades, more and more refined simulations of the universe's large-scale structure and seeing how it evolves. So that's what I'm showing here is a slice of the illustrious TNG simulation, where you see here in this panel here at the top, the dark matter column density and the gas column density here on the left-hand side. And finally, you see the stellar column density here in black. And you can see how they evolve with time under the influence of gravity, that structures are getting formed and to create ever more massive structures. And what I'd like you to focus in right now is on the left-hand side, you see this is the temperature of the gas as a function of time. And you can see, so redder colors here correspond to higher and higher temperatures. And you can see these shocks which propagate throughout the medium during as time evolves. And these shocks are heating up the gas around, such that we get progressively higher and higher temperatures in the medium that is filling this large-scale structure to temperatures in excess of 10 million degrees, which are the red colors here. So here you see at this time at this time we have two main halos, which are now in the process of forming and eventually virializing, such that we get this corresponding gas temperature that gets hotter and hotter. Okay, so what we know from this model is that actually the formation process of these dark matter halos in the universe is very homogeneous. It's the same in every structure, independent of its size. And this is something that was highlighted originally by Navarro, Frank, and White in these seminal series of papers in the late 90s. And here you can see this is on from their paper in 1997, where you see the density profiles. So this is the log of the total mass density as a function of radius in formed halos in different masses. And here there are some of these curves represent dwarf galaxies, some other curves represent the most massive clusters. And you can see that if you scale them appropriately, they look very much the same. So if someone tells you that dark matter is just something that was invented and can match any observation, that's really not true. The cold dark matter paradigm makes very clear predictions on what the shape of halos in the universe should be. And they say that it should follow this functional form here, Navarro, Frank, and White, which has two parameters, the scale radius Rs and the normalization density ρS. And even more than that, the CDM framework makes some clear predictions on how the parameters of this NFW profile should be as a function of the halo mass. This is what is shown here on the right-hand side, where you have the concentration parameter, which is the ratio of the scale radius Rs to the virial radius of the system, which is here, we use the R200 as a proxy for the virial radius of the system. And this concentration parameter, you can see that for it's higher usually for lower mass halos than for higher mass halos, because it actually traces the formation history of halos, and lower mass halos were formed earlier in time. So the dark matter has concentrated more as it evolves. So not only does the CDM scenario predict the shape of the dark matter profiles as it should be on average, it also says how the parameters of the NFW function should evolve as a function of time and as a function of halo mass. So those are very clear predictions. And if those predictions don't match, then we have a problem with the CDM scenario. And when we look at this type of profiles in the case of dwarf galaxies, we actually see that there's some potential issues there. And that is what I'm highlighting here is what is called the core cusp problem, where you can see on the right-hand side, this is the rotational velocity of a couple of dwarf galaxies, the stars in a couple of dwarf galaxies, as a function of distance from the core of the dwarf. And you can see that the observed rotation curve here, they follow this much flatter shape here compared to the expected NFW shape, which is here in black. So that's not a general phenomenon. Some dwarfs are following the NFW, some are not. But basically, there is some diversity there that could potentially not be captured by the standard LambdaCDM scenario. On the other hand, dwarf galaxies are very complicated systems. They're poorly understood. Baryonic effects are very important in these very low mass objects, because basically a single supernova at high redshift would be sufficient to expel all the gas from a dwarf galaxy, or vast majority of it, such that there are complicated processes taking place like adiabatic compression or expansion as a reaction to what's going on with the gas, such that dwarf galaxies are in principle not the very vast systems to try to look for deviations in LambdaCDM. But anyway, if those deviations are real, then there's a number of possibilities which have been put together to try to solve this forecast problem. And one of them is warm dark matter. So in that case, we imagine that the dark matter particle has a mass of the order of a few keV, up to a few tens of keV. And in that case, the dark matter particle is actually mildly relativistic at present time, such that small structures are not able to contain it, and it will free stream out of it and will change the properties, especially of small structures. Another possibility is self-interacting dark matter. Then in that case, you imagine that instead of being collisionless, the dark matter particles have a non-zero, non-vanishing interaction cross-section. Then in that case, we are going to alter as well the properties of the dark matter profiles because of Coulomb collisions between particles. And finally, the last possibility is that the gravity, as we understand it, may actually not hold in the very low acceleration regimes that we are probing here, which are many orders of magnitude lower than what we can probe on Earth. And the main proponent of that is what we call MONF, or modified Newtonian dynamics. And this has been shown to be very successful at reproducing the rotation curves of spiral galaxies. I'll come back to that later in the talk. So those are several hypotheses that have been put together to try to explain this core cusp problem. And of course, they will make different predictions for what we should see in the case of the most massive clusters that we see today. One way to parameterize these dark matter profiles that does not make the underlying assumption that everything looks like what cold dark matter should be, and that has been proposed more recently, is this ASST shape. So it has been actually proposed in a number of simulation papers that this profile shape here, which has one more parameter, is doing a better job at reproducing the shape of the profiles that we see also in CDM. So it has one more parameter, which is this quantity alpha here, that is regulating how curved the profile look like. And just to give you an idea, this is some just model ASST profile. When you change the value of alpha, then you see that alpha equal 1, it has a very flat core, while alpha equal 0.1 is basically a pure power law with very small curvature from the core to the outskirts. And what has been realized also recently is that this alpha parameter is sensitive to the conditions that they were in the early universe before the matter has collapsed together and the halos have started forming. And this is in the form shown here in the form of this parameter NS, which is the slope of the power spectrum of fluctuations in the very early universe. And you see that if you change this parameter NS, then you change the shape of the profiles as they form later on. And here this is what in comparison with the NFW form, and you can see that it actually does a pretty bad job at representing the shapes as we see them in the case of different NS compared to the classical one, which is this 0.96 here. While for the ASST profile is actually has enough flexibility in order to reproduce the shape of this profile independently of the value of this primordial power spectrum. So the ASST parameterization is nice because it allows us to give some really some constraints on the shape of these profiles beyond just the assumption of LambdaCDM. So I guess you get where I'm going with this. What we've tried to do in this work was to try to measure the properties of the ASST profile. And what we used for this? Well, this was already in the title. We've used galaxy clusters because they are the largest concentrations of dark matter, right? They can contain up to 10 to the 15 solar masses of dark matter. So you can see here this wonderful Hubble image of the cluster MAX 0416, where you have the galaxies here in the background from the HST, and we have the gas that is shown here in purple, and the gravitational potential here reconstructed using gravitational lensing in blue. So I won't be talking much about gravitational lensing in this talk, but if you're interested, you can of course ask me later on. But then the point I want to make here is that because there are these very large concentrations of dark matter, they are the best place to search for deviations from the LambdaCDM scenario. So the way that we adopted, the method that we adopted to measure the properties of the gravitational field was the hydrostatic equilibrium method. So the idea is that we assume that the gas is in equilibrium, its pressure is in equilibrium with its own gravity. If we have, in general, if we have a gas which is has an inviscid property, so it has a zero viscosity, then we can write its evolution in terms of the Euler equation, which is written here, where these terms here depend on the velocity field of the gas. And if the system is in equilibrium, then the velocities are on average zero, so this term vanishes. And we can write the hydrostatic equilibrium equation, which is a well-known equation here on the right, at the bottom. And if we are able to measure the pressure of the gas and its density, then you can see that based on that, we can reconstruct the gravitational field file here. Okay. And to do that, we have employed X-ray observations because they are the most direct probe, of course, of the gas in clusters. And they are proportional to the integration along the line of sight of the square gas density. But we have also used another probe, which has been gained a lot of traction in recent years. That is the Sunyaev-Zeldovich effect. And that is the Compton scattering of electrons, of photons, CMB photons, when they pass through the hot electrons of the cluster. When they do that, they get a small kick in energy, and this small kick is proportional to the pressure of the gas integrated along the line of sight. So if you've got those two probes there, then you can reconstruct the temperature, the entropy, and finally you can solve this hydrostatic equilibrium equation, and you can get back to the gravitational potential. And to do this, we have employed the XCOP project. XCOP stands for XMM Cluster Outskirts Project. This is a very large program on XMM that I was leading a few years ago. And it's following the Planck clusters with the highest signal to noise in the Sunyaev-Zeldovich, such that we know we've got very good Sunyaev-Zeldovich measurements of these systems. And then we cover up these large regions around with XMM, such that we also get the very good measurements of the gas density profiles. Here are the Sunyaev-Zeldovich maps of these systems from Planck that were published a few years back now by Anna Silvia Baldi. We have actually another different reconstruction of these maps that was made by the Planck team and by Etienne Pointe-Couteau's team. And by combining them, then from the X-ray, we get the gas density profile. And you can see there, you see we can do that over a very wide range in radii, more than 2 orders of magnitude in radii. And then by combining the Sunyaev-Zeldovich effect here with the pressure, with the temperature that we get from the X-ray by fitting the X-ray spectra, then we can get back also, we can get this sort of pressure profile over a wide range in radii. You can see then we can solve the hydrostatic equilibrium equation point by point. So to do this, the first thing we need to do, of course, is to check that our two observables, which are independent from one another, that they are consistent, and they are. So here on the left-hand side, I'm showing this parameter eta, which is the ratio of the pressure that we get from the Sunyaev-Zeldovich effect to the one we get by multiplying the X-ray spectroscopic temperature by the electron density. And you see that this ratio is consistent with 1, meaning that our two probes are nicely consistent. And then what we are introducing in this series of papers is a mass reconstruction technique, which uses a Bayesian forward-fitting approach. And what we are doing is we are starting from a 3D structure, which with a given shape. And then we are projecting along the line of sight, because the images that we've got both in X-rays and Sunyaev-Zel'dovich, of course, they are integrated everything along our line of sight. And then we are smearing with the PSF of the instrument, such that the sharp details that we can see, they are actually smeared out. Then on top of that, we have unrelated emission, which is background emission, which can be either instrumental or true background. And finally, what we get in X-rays is a Poisson realization of this image, such that we get a pixelized image like this. So what we are doing is to take all this problem in a forward way, where we start from the 3D structure, apply all this projection, PSF smearing, and so on, and fit that directly to the Poisson images that we get. And here is an example of application of this technique. On the left-hand side, you have our surface brightness profiles that are measured by XMM, and the model that is convolved with the PSF is shown here in green for this cluster labeled 1795. The PSF deconvolved profile is the one that is shown in blue. And on the right-hand side, this is the temperature profile, where the red points here are the spectroscopic X-ray temperatures. So they are projected in 2D, while the orange points here are obtained by dividing the pressure we get from the Sunyaev-Zel'dovich effect by the X-ray gas density. So this is here a 3D temperature, and you can see that our model, which is in 3D here in green and in 2D in blue, is doing a good job at reproducing our data. Then we apply several different reconstruction methods. So first of all, we have this cyan curve here. These are the pressure profiles with the cyan points. That is a non-parametric Gaussian process reconstruction, which tries to be as close as possible to our data. Then we have a forward-fitting approach, which is shown in orange, where we use a parametric form for the pressure profile, and we adjust that to the pressure profile, and then solve the hydrostatic equilibrium equation. And then we have those two curves here, ASST and NFW, which show the result of assuming that the true mass profile follow a given parametric form, and then integrating the hydrostatic equilibrium equation to predict our pressure and fit that to the data. And these are the mass profiles that we reconstruct using those three different techniques. The points here are the non-parametric points evaluated. That's the radii where we have actual data points. And these are shown with the various models. These are shown in comparison with the various models. Okay, and this is now for the same system. What we can do in terms of the ASST model that I showed before. The ASST model has a lot of flexibility, but we are able to reconstruct here this parameter mu. This is 1 over the ASST alpha. You see that we can get this very good constraints on this parameter there. That is the parameter of interest for this study. Okay, so if you're interested in the technique, then I will refer you to those papers, and just let you know that we have released our codes together with this series of papers. So if you're interested, you can check out these in the form of these two Python packages that are referenced here. There's a full documentation of it, so you're welcome to use it if you're interested. So now digging into the results, this is what we've done first was to compare the results of the reconstruction with the various mass models with the non-parametric reconstruction. And this is shown here on the left-hand side for the Navarro-Frank-White, and on the right-hand side for the ASST model. And this is the ratio of the model to the non-parametric point, or the inverse, or the non-parametric point to the model. And what you can see is that, especially in the central regions, the Navarro-Frank-White model, there's a lot of scatter in these points there, where there is somewhat less scatter with the ASST model. So there is a bit more variety in these profiles than what NFW can capture. But on the other hand, if we make an average of these points for the whole sample, then here the red points are the average of the non-parametric points for all our systems. and this is compared with the mean INASTO, mean NFW profiles, then you can see that on average, they are tracing each other very nicely. So the NFW, which is the prediction from LambdaCDM, is a very good description of our data. So far, CDM seems to hold. Then another thing that we can do is that since we have such accurate data, we can measure very precisely the concentration of the NFW profile. And so each of these small ellipses here is a measurement of the concentration on the y-axis and of the mass on the x-axis. And then we can measure the average concentration and its scatter in our sample and compare that with the predictions of LambdaCDM simulations. So this is our mean value of the concentration and of the mass. And these are the predictions from LambdaCDM, which are spot on. So again, looks like the structural properties of the galaxy clusters as we see them are perfectly consistent with the LambdaCDM scenario. So with the idea that the dark matter is cold and non-collision. Now, as I said, we have assumed that here that CDM, so in that case, that the self-interaction dot cross-section is 0. But then what happens if we relax that assumption and let the self-interaction cross-section vary? Then what's going to happen is that there is going to be Coulomb collisions between dark matter particles, especially in the central regions of halos where the densities are high. And then in that case, the Coulomb collisions are going to homogenize the velocity field of the dark matter, and it's going to cut out the core where the velocities are lowest. So we get profiles of the dark matter halos that will look like the red curve here instead of the CDM predictions, which will look like the gray one here. And what we propose in this paper is that we can use the alpha parameter from the INASTO model to constrain the self-interaction cross-section. So as we've said, the INASTO alpha parameter allows us tells us about the curvature of these profiles. So the more curved the profile, the higher the INASTO index. And then in that case, the higher the self-interaction cross-section. And what you can see here in this plot, these are simulations, again, cosmological simulation, but this time were done by changing the dark matter self-interaction cross-section. So those various points here, so black here is still CDM, and then you have these red, magenta, and cyan points, which are the result of cosmological simulations changing the dark matter self-interaction cross-section. So this is for a cross-section of 0.1 centimeter square per gram, 0.3 centimeter square per gram, and 1 centimeter square per gram. And these are all the individual halos and the fitted value of alpha INASTO to these simulated halos. And you can see now this is the mean value on the right-hand side, the mean value of alpha as a function of the self-interaction cross-section. And you can see that it's lower in CDM than in a self-interaction dark matter model. And when you increase the dark matter self-interaction cross-section, you increase the value of alpha. Another thing that we looked at in this plot is we checked how our model for baryonic physics can affect the results on these measurements of alpha. So dark matter in simulation is fairly easy to model, but baryons are complicated because there's lots of additional effects that we need to understand. And here we have those two other points in yellow and in green, which were different CDM models, now where we changed the baryonic physics. And you see that the results in terms of the measured value of the INASTO parameter basically don't change. So this means that this method is robust to the choice of the baryonic physics that we put in our simulations. So now coming back to the observations, here are the measured values of alpha for all our 12 systems. And you can see on the, so the blue points are the individual measurements, and the black here with the gray area is the mean value across the sample with this uncertainty. And we notice immediately that there seems to be two groups of systems. There's this group which clusters around here with this value around 0.2. And then there's a few systems that are strongly deviating from this value of 0.2 that are shown here. And we looked into this with a bit more detail. And what we realized is that all these systems that are here are actually dynamically active systems, which are probably currently experiencing a merger, such that the gas distribution is disturbed compared to the dark matter distribution because the gas is dynamical, such that the main effect here is probably that we don't really know where the center of the potential well is, and it doesn't lie at the same position as the peak of the gas density. Then in that case, of course, if we are measuring our profile with the wrong center, then we are going to flatten our measured density profiles, and we are going to get more curved profile compared to the true one if we actually knew where the center was. So what we did was to select only the regular X-ray clusters, the ones for which this parameter W, which parameterizes the distribution of the photons. So that the lower the value of this W, the more regular the photon distribution. And we select only the ones which have a low value of these W parameters, such that we know that we can confidently make an inference on the value of alpha in these systems. And then this pink curve here shows the mean value of the systems that have a low value of alpha, of W, sorry. So the X-ray regular systems. And now what we've done was to compare the value of these of alpha that is measured in these systems with the same thing in the numerical simulation by changing the dark matter self-interaction cross-section. And why? So here, what we've done also to make sure we compare apples with apples is that we have selected only the relaxed systems in the numerical simulations, because we've also seen that there's a difference in terms of the measured alpha parameter from the relaxed system to the unrelaxed ones. So here is the result now. Here is the mean value of alpha in our data. This is for the full sample. This is for the X-ray regular systems only. And now this is the mean value of alpha in our 3 runs, CDM and then the SIDM with changing cross-section. And we can see that our results are consistent again with the CDM scenario. And value of large values of cross-section are in strong tension with our measurements. And so what we've done was to take our simulations and fit a relation between the value of alpha and the self-interaction cross-section that you can see here. And these are our measurements, which this allows us to translate our measurements of alpha into an upper limit on the self-interaction cross-section, which is what you can see there now for the full sample in red and for the regular subsample in blue. And you see that our upper limit is set an upper limit of 0.13 centimeters squared per gram at 90%. And this is about 10 times deeper than what you can see with individual merging systems like the bullet cluster. So this is a really deep upper limit that is one of the best currently in the literature right now. Okay, now one more thing we can do is that for our subset of systems, we have full measurements of all the baryonic components, meaning we don't just model the full gravitational potential with a given parametric shape, but we also have measurements of the gas density profile, of course, because we're observing them in X-rays. And we have measurements of the stellar content of these systems. So this is shown here. This in green is the central galaxy, brightest cluster galaxy, BCG, while in blue are the satellite galaxies that are populating the cluster. And what you can see is that what we are fitting then is the pink curve here, which is the what's left, right? So basically, we know what the gas is, we know what the stars are, so we can fit what's left on top with the dark matter profile. So now we are fitting the dark matter only in this case, and we can study the interplay between baryons and dark matter. And on the right-hand side now, what I'm showing is the fraction of baryons total, so the fraction of gas plus stars divided by the total mass as a function of radius, has this somewhat complex shape. But the important thing is that at large radii, it converges to the baryon fraction of the universe, which is given by the ratio of omega baryon to omega matter, with the exception of one cluster here. If you're interested, you can ask me later about this one. And then what we can do from that is we can study, as I said, the interplay between baryons and dark matter. And the main reason why we wanted to do that was we were triggered by this results by McGo et al. A few years ago, which used a large sample of disk galaxies where they measured the rotation curves. And in these rotation curves, they measured the observed acceleration from the rotation velocity. And then they measured again the stellar content, the gas content, and they related this with one another. And they could see that there's this apparently tight relation between the observed acceleration that when we see the velocity from the rotation velocity of the stars and the baryonic acceleration, so that is given by what we see, right? So from the baryons, we can compute how much acceleration we expect to see in Newtonian gravity, and that is what is shown on this axis. So they seem to say that there is a tight relation between the two, which incidentally matches very well with the MOND formula. So the modified Newtonian dynamic formula. So if that is correct, then of course it's a very fundamental thing, because it would tell us that just by changing our law of gravity below some threshold here, we are able to reproduce the behavior that we see in terms of the observed gravitational field, such that would be really consistent with the idea that it's really our theory of gravity that needs to be changed, and not we can stop searching for dark matter, right? So we were triggered by that, and we wanted to see whether that works as well in galaxy clusters. And here is the result. And so you can see immediately that we are somewhat off. So on very high acceleration here, with this is the regime where we are inside the central galaxies. Again, the stars are somewhat dominating. And then when we move outside, at the same expected level of baryonic acceleration, the actual acceleration that we detect in our systems is actually quite a bit stronger than what this radial acceleration relation would predict. The one that, so if it were indeed a fundamental property of gravity, then we would expect this to stand close to the black line here. While at larger radii, lower accelerations, we kind of catch up with this predicted behavior. So our conclusion was that this radial acceleration relation is not universal, and we had a referee who was a very convinced Mondian advocate. So what he told us was that, oh, but what if there is actually a missing mass component in clusters only that does not exist in galaxies, right? So in galaxies, we'd be able to see all of the baryonic components and our radial acceleration relation consistent with MOND would work out on its own. In clusters, there's actually a missing component that we do not yet see. So, I mean, you may say that it's a somewhat ad hoc possibility, but nonetheless, we searched for it. So we thought maybe, what if this missing mass component exists? Then what profile should it have in order to reproduce our data under the assumption that that MOND is true, right? And that is shown here by these pink curves here for each individual systems. So this would be the mass profile of the gas in green, mass profile of the stars in cyan, and the additional mass that we would require as a function of radius here in cyan. And the important point that I want to make here is that this falls off at large radii. This is a cumulative mass profile, not a differential one. So it means that the mass that you need to reproduce what's going on there should actually somehow disappear at large radii in order to match the behavior that we see. So this is a non-physically decreasing mass profile on large scales. So clearly our data are not consistent with MOND even under this assumption there. Okay, now moving to where we would like to go in the future and where Athena is going to help us so much. If you remember what I said in the beginning with about the technique that we put forward here, this hydrostatic equilibrium technique, we make a strong assumption there. And the assumption that we make is that the velocity field is negligible. Okay, so the true assumption is the Euler equation that I show here. And in order to get to all the results that I've shown you so far, we assume that this is 0. But what if it's not? And actually, numerical simulations predict that it's actually not. So this is the result here of a numerical simulation, so a set of numerical simulations at high resolution by Matteo Angelinelli. And what he has shown is that the velocity field looks like something like this over that's one slice of a given systems. So the gas is moving. So we see there's coherent motions like this where we have a big chunk of gas which moves towards at a given velocity. And then we see these random motions that looks like this, which are turbulent motions injected by the mergers, the fact that our systems are not completely relaxed. Okay, so then these are attempts that we did in the paper in order to try to disentangle those two components, the turbulent velocity field on the one hand and the bulk velocity field on the other. And we are especially interested in the turbulence term because if it's random, then it will act as an extra pressure term on top of the thermal pressure, and it's going to change our measurements of the masses that we get, the gravitational field that we get under the assumption of hydrostatic equilibrium. Okay, so what we want to do to get beyond what we've done so far is to be able to constrain this velocity field. And of course, we had the first attempt at this a few years back from the Hitomi telescope, which observed the Perseus cluster, so the brightest X-ray cluster in the sky, and after a few days of operation, then we turned on the microcalorimeter on Hitomi, and it produced this absolutely amazing spectrum of the central regions of the Perseus cluster, where you see here, this is the central AGN of Perseus with the bubbles and the expanding material. And even though we know that there are lots of motions going on in this system, what Hitomi has shown is that the line broadening there that would be consistent with the random velocities of the gas along the line of sight is just 164 kilometers a second, which is I mean, so the sound speed in a system like Perseus is more than 1,000 kilometers a second. So these are strongly subsonic motions. And then if you turn this measurement here into an estimate of the turbulent velocity, of the turbulent pressure support, sorry, then you get that this is approximately 4% of the thermal pressure. So it's a small correction, at least in the core of Perseus. But that's the important point. We are looking at one system in a very special region. How do we know that this stands over the wide, very large regions that I looked at? If I compare with the type of scales that I showed you before in the case of the Eckert clusters, this is really, really tiny, the innermost regions. So it doesn't tell us anything about the amount of velocity fields at on the large scales where we can do such a nice job with the Eckert measurements. Of course, then hopefully next year, we are going to get a new shot at this with the CRISM satellites, which is the refly of Hitomi, as you know. And CRISM will, among the performance verification targets of CRISM, there will be the Hubble 2029 cluster that I'm showing here, which is actually one of the Eckert clusters. And what we will do is we will measure, these are three different fields of the SXS calorimeter, which is now called Resolve on CRISM, with one in the core and then three measurements along those arms. And this is R2500. So we are still quite a bit in the central region of the system. But even then, it's going, as you see, it's difficult to cover a large region of this object with CRISM because it has such a small field of view and such a small effective area. So this is the simulated spectrum we expect to get with CRISM in the outermost field, so this P3 here. And this should tell us about the profile of the turbulent velocity across the system. But of course, it's not enough, right? Because we are limited to regions that are still somewhat close to the central regions of the system. So there's not enough to estimate an impact on large scales. And field of view is small and effective area is quite small. So what we really need, of course, is the XIQ. And I'm showing here, I'm stealing this slide from the work of Mauro Roncarelli back in 2018, where what he's done there was to take a simulation. He put a simulated cluster at a fiducial redshift of 0.1, and he had the maps of this system in the simulation with the emission measure, so that's proportional to the surface brightness that is shown here, the temperature structure there, and the velocity field here, and the velocity dispersion. And those are the true maps that were put into the simulation. And that's what XIFU retrieves in the simulation. As you can see, there is a really striking correspondence between the two. And the XIFU has the necessary capabilities to measure the velocity field very accurately. And even the velocity dispersion, it can map it over a very large scale in the system. So what we need in order to get back to increase our accuracy on these dark matter profiles is an instrument like the XIFU, where we are going to get these velocity measurements to very high precision. Okay, so I'm willing to work with all of you as much as I can in order to make this dream come true. And I will leave you here with my take-home message. And thank you very much for your attention.
Thank you very much, Dominique. Really interesting talk and lots of really very interesting results. I think you've done an impressive job of killing Mond there. Have we got any questions? If you'd like to put questions through the Q&A chat, or I think people may be able to raise hands as well. Any questions? I guess.
If it's okay, I'll start off, Judith.
Okay.
You were talking about the clusters that you eliminated because they were obviously going through mergers, and so you couldn't get a centroid or a good centroid for those clusters. I was wondering, since you also have some really good simulations, and we know that it's really not the case that clusters are either recent mergers or not recent mergers. Basically, probably mergers are going on at some level all the time. Could you treat that as a systematic uncertainty term that basically it's not possible to know the actual center? And if you did that, do you have any feeling for how accurately we can measure the center in, say, an average galaxy or average cluster where you're not quite sure when the last merger was?
Yeah, I completely agree with this point. So, in fact, what we would like to do now, in order to get a little bit beyond this work, is to take our simulations, these are the ones that are shown here, from also varying the self-interacting dark matter cross-section. And what we'd like to do is to create mock observations, mock XMM observations of the systems that we simulate, and then apply our methodology to the simulated systems, such that this would give us a real comparable, a real comparison point, that even in the case where the center is not really known, right? Because it would be the same in the simulation as well, where we not really know where the center is. So this would potentially allow us to extend this work to larger sample, irrespective of the dynamical state of the systems. I hope that answers your point.
Very well, good idea. Thanks very much. And the next one, talk, obviously.
So I can't see any hands at the moment, so maybe I will ask a quick question. So the constraints that you were getting on the cross section for self-interacting dark matter, you mentioned that those were much better than from bullet cluster type calculations and so on. Can you comment on sort of how much further you think it may be possible to push that down, and whether or not that sort of whether that's ruling out particular particle physics models, or quite what that then tells you?
Right. Yes. Okay. So, okay, we can go a little bit further, of course, if we shrink the error bars on this plot, right? So if we shrink the error bar on alpha, then we see we can go down a little bit on sigma. However, you see that this curve here is fairly steep, right? So it means you need to make a very big improvement in terms of the precision on alpha in order to get significantly deeper on sigma, right? So I don't think that, okay, we can do a somewhat better job, as I said, by increasing the sample size and getting rid of this assumption that we need only relaxed system and so on. So we can get maybe a factor of 2 on that front, but maybe not that much deeper, at least so far. However, coming back to the particle physics, to the link with particle physics, the point is that if you want to solve the core cusp problem, the one I've shown, talked about at the beginning in dwarf galaxies, so the fact that we see flatter profiles in the core of the dwarf galaxies with respect to an FW. If you want to solve that with self-interacting dark matter, then you need cross sections which are the order of 1 to 5 centimeters square per gram. So larger than what we put here, the upper limits that we put here. On the other hand, if you look at the particle physics model which predicts some self-interaction, non-vanishing self-interaction cross-section, then many of them most of them, I would actually say, predict that this cross-section is velocity dependent. And when you look at a cluster, you have typical velocities of 1,000 kilometers a second for the dark matter particles. While if you look at the dwarf galaxy, then you go down to some 10 kilometers a second, or a few tens. So if the velocity, if the self-interaction cross-section is a strong function of velocity, then it may be that you can still reconcile what the core cusp problem with self-interacting dark matter. But so I think that in this respect, the technique that we are proposing here is very promising, because you can apply it eventually not just to the most massive clusters, but you can try to do this going down in mass, especially going down to groups. Mm-hmm. And then you can do a similar job at group scale. And you can try to eventually set constraints on this velocity dependence. Hope that answers your question.
Yeah, no, thank you. Yeah, no, that's really, really interesting. Yeah, sounds quite promising. Any other questions? Oh yeah, Didier?
Yes, thanks, Dominique, for a very interesting and a very rich talk. I mean, I know we all need to dream, but we may be facing slightly less exciting dreams in the near future, unfortunately. Thank you, Isa, for this. If you were to dream a little bit less in terms of about angular resolution, spectral resolution, field of view counts, in which parameter, what would be your ranking of this performance parameter for this particular science?
Yeah. Okay, so I hope we can do something, right? To answer, I think to me the answer is clearly the field of view that we need to optimize. And the point is, it's this point here. If our field of view is too small, then it's going to take us forever to map the velocity field in a single cluster. So if I were to choose, then I'd say I'm fine with somewhat degraded spectral resolution, for instance. Like, if instead of 2.5 eV, we have 5 or 6 eV, I'm fine with that. For me, it's sufficient to do what's required there. But if we shrink this field of view too much, then of course we lose all of it, because it's going to take us forever to cover significant areas with the XIFU. So to me, that would be my own personal wish list, of course. Not that I would not benefit from having 2.5 eV resolution, of course. We all want that. But if we have to compromise somewhere, then I would rather compromise on the spectral resolution or on the spatial resolution rather than on the field of view.
Okay, I think that's, thank you for this answer. That's very interesting. Just for your information, we are not considering degrading the spectral resolution at the moment beyond 3 eV. We want to stay less than this, and making sure that this new performance will have enough margins to simplify the requirements at some critical interfaces. So if those interfaces are mastered well, we may go below that number, which we may be able to set today to 2.8, 2.9 eV, or possibly a bit less than this. And the field of view is much more challenging to keep because it drives the number of retards of radar channels and the thermal loads at the cold stage. So
I know it's challenging, yeah.
We are not going to cut it down to, I mean, we want to preserve the flagship capability of Athena, but it's going to be tough to retain the 5 arc-minute field of view, but we are doing our best to safeguard that parameter, because I agree with you, it's one of the most emblematic performance parameter we want to retain.
Yeah, I mean, of course, if we cut the field of view, but if we keep the same resolution and effective area, spatial resolution, I mean, then we can always say, instead of looking at objects like the one I'm showing there, we can try to observe systems that are a bit more distant, and then they are of course smaller on our field of view. But then it means, of course, that they are also fainter. So we have to spend more observing time on one system, right?
Yeah, I think we want to retain the pixel. I mean, of course, the angular resolution will be set by ESA, but at the moment they consider 8 arc-seconds as being demonstrated. They will probably work beyond that. For us, there is no reason to change the pixel pitch at the moment, so we will remain with pixels of the order of 5 arc-seconds, matching more or less well the PSF of the optics, which ESA will set, but today 8 arc-seconds seems to be doable for them. Yeah. So it will be a matter of observing time. Okay, well, thank you, Dominique. I have to go.
Yeah. So what I'd like to stress here is that it's going to be a breakthrough no matter what, the XIFU, because one thing that is not shown on the picture here is the CRISM spatial resolution, which is 1 arc-minute. So doing something like this with CRISM, you can forget it. Even with the descoped Athena, we will do some fantastic things.
Yeah.
Thank you, Dominique. Have a good one.
Yeah. So there's a question from Johan Comparat. I think if you'd like to ask your question, I think you should be able to.
Yes. Can you hear me?
Yeah.
Yeah. So yes. Thank you for the presentation. Very, very nice. I was wondering about the concentration mass relation. Since you have many points, have you looked at the full distribution of concentration at fixed mass? And compared to simulations, it's quite a broad distribution in simulation. So could we have equivalent from the data?
I mean, it's just 12 points here, right? Okay. So what we have looked at is the scatter in the mass concentration relation at the mass, or at the mass around 10 to the 15. And this scatter, we've compared it with the scatter in the simulations, and it's perfectly consistent.
Oh, fantastic! And so you are not so in this plot, is it selected against mergers or
no? Mergers? That's the full sample.
Excellent, thank you.
Do we have any more questions? I can't see any more hands or any more questions at the moment. No, so if not, then many thanks again to Dominique for a really great talk, and thanks to everyone for coming along. Our next talk is on the 26th of October, and we'll have Barbara DeMarco talking to us about the innermost regions of accreting black holes. So I hope that many of you will be able to come along to that one as well, and hopefully see you then. Thanks very much, everybody.
Thanks very much.